Good. So we'll continue talking about continuity today. We're in section 4.3. I haven't opened up the wiki yet for 4.3, but I'll do it after today's class. What else wanted to tell you about? The department has already come up with guidelines for exams. So I know our next exam is still going to be a while, but I mean, we have a couple of weeks, I think, maybe a bit more, but it's going to be a take-home exam. So we'll supply more details. You'll get it from Canvas, and you'll upload your written solutions on Canvas as well. So I'll provide more details, and I'll post on our Canvas page when we get closer to it. All right, but I just want to give you a little update on that. Okay, so let's recall what we were doing. We were talking about continuity, and specifically we went over this theorem right here, which is how we can characterize continuity. And we have different possible choices here. So in one of them, we have the traditional one, which is this one, number one. So for every epsilon, there is some delta, such that if your value x is delta close to c, then your value f of x is epsilon close to f of c. Then we rewrote the same exact concept, but with neighborhoods. This is a restatement of number one, only talking about neighborhoods, meaning you can find a neighborhood such that if there is an epsilon neighborhood, for every epsilon neighborhood, there is some delta neighborhood such that whenever x belongs to the delta neighborhood around c, then f of x belongs to the epsilon neighborhood around f of c. This, in other words, means if x is close to c, how close? Delta. Then f of x is close to f of c, how close? Epsilon. Then we saw number three, which is best for us because we already know a lot about sequences. It says that a function is continuous is if every sequence that converges to C has the property that the function applied to the sequence converges to f of C. And we also have this number four, which is sort of the traditional definition of continuity that you maybe know from calculus. And that one applies quite well if we have a limit point, because for isolated points in the domain, this limit makes no sense. It cannot be defined. But these other definitions make perfect sense. Okay, so we were doing this a week ago. We didn't have a class on Tuesday. And we finished by looking at this example of a function, the function x times sine of 1 over x, and we showed that it is continuous at 0. In fact, everywhere. The other points we'll later talk about how we can derive them, but we only checked at 0, which is the weird point over here. Is there a question? Okay, and we saw that polynomials are continuous. We saw that rational functions are continuous in their domain. And today I want to continue with talking about this example 4.3.7. Okay, so let's talk about that. So this is a function that you maybe seen already in the exercises from section 4.2. And if you haven't, then you'll learn about this function for the first time right now. So we're talking about the function least largest integer. So the book calls it h of x and denotes it this way. But in other books, maybe you've seen it before, and then it's also denoted this way. And it's called the greatest integer function. and also known as floor function. Okay, and here's how it's defined. So h of x is defined as the largest integer n such that n is less than or equal to x, right? So let's provide a few examples to understand this function. So if we, for example, h of, say, well, 3, if you pick an integer, well, then the integer itself is less than or equal x, and it's obviously the largest. So for every integer, you get the same number, right? So h of 3 is 3. But if you pick something in between, like say h of 3.7, then we're looking for an integer that is smaller than 3.7, but as large as possible. It has to be 3, right? And now maybe you can see why we call it the floor function, because essentially we're dropping out the part that is fractional, right? The decimal, so to speak, right? It's like keeping only the integer part. And here's another example. H of pi, well, that's going to be 3 as well, right? All my examples are 3. Now, for negative numbers, you need to be careful because, remember, we have an order in here. So if we look at, say, h of negative 2.4, what would this one be?
Negative 2?
Yes. Or is it? So let's do a little drawing here. So I have as options. So Petro says negative 3. So and I heard negative 2 as well. So let's do a picture here. So here's the real line. And so here's 0, here's negative 1, here's negative 2, here's negative 3. And right now we're looking at negative 2.4, right? So that's this number right here. So number over here, negative 2.4, right? And what number are we talking about? So we want one that is smaller than negative 2.4, right? Smaller than negative 2.4, but the largest integer. So it cannot be negative 2, right? Because negative 2 is bigger than negative 2.4. It has to be smaller. So it is actually negative 3, like Petros said, he's correct, right? So you need to be careful with negative numbers, right? Because negative numbers, so it's not really take out the fractional part for negative numbers because of the way we define it, right? So we're looking at the number from the left, and we're looking at to see what is the largest integer behind it, okay? All right, so let's come up with the graph of this function. So let's graph this function. How would the graph look like? Let me put my axis here. Right, and then what do we have? Well, see, between 0 and 1, it's all 0, right? Including 0, so like this, and then there's a hole here at 1, right? Then between 1 and 2, so the greatest integer function at 1 is 1, because that's an integer. And then any number between 1 and 2, it's only 1, except for 2, right? So for 2, it grows 1 unit, right? And it continues this pattern, correct? Let me do a bit more here. So the next one will be from here to 3, open here, and then from here to here, open here. Let's do some negative ones. How about between negative 1 and 0? Well, like we said, right, it cannot be negative. I mean, it's going to be negative 1. It's not 0, right? It's going to be negative 1, so including negative 1. So it's like this. and so on, right? So it has this nice pattern of being like a stair, right? Okay, good. So now what we want to show is the continuity. What we want to show right now are the continuity properties of this function. Specifically, we want to show that it is not continuous when we find an integer, and we want to show that it is continuous for all the other numbers. All right. So let's do that. So we want to show that h of x is not continuous at m, an integer, x equals m. And on the other hand, so show that h is continuous at every x that belongs to the reals but is not an integer, like that, right? Okay, that's what we want to do. Okay, so what is our best tool to show something is not continuous? And if you remember, we had actually a great corollary to our theorem about sequences, and that's what I recommend essentially to show that anything is not continuous. Let me show you on the page. So, I mean, on the book, and it's right here. Criterion for discontinuity, this one over here. What does it say? Well, it says that you can show something is not continuous if you find a sequence that converges to your number such that the function evaluated at the sequence fails to be convergent to f of c, right? If it's not going where it's supposed to go, that's it. And you only need to do it with one sequence, right? So actually checking that something is not continuous is easier than checking it is continuous, because we only need to supply a sequence, right? And so now let's go back to the page and see if we can come up with the right idea for a sequence here. So what kind of sequence? Say, let's do it for the number 2, right? Say we want to show that right here at 2, the function is not continuous. What do we want? Well, we want a sequence of points such that the limit of those points is not approaching f of 2. Now, f of 2 is 2. We know it right here, right? So f of 2 is right here over here too. So what kind of sequence should we choose? Well, let's see. If we choose numbers that are bigger than 2 and getting close to 2, those guys are all going to be 2's, right? 2, 2, 2, 2, 2, 2. So those guys are not going to work because they're all going to be 2's. And that's exactly what we want. But to prove that it's not continuous, we want a sequence that, yeah, so Petrus has said 2 minus 1 over n. That will work, right? So we want anything that approaches 2, but from the left. Why from the left? Because all these numbers are actually equal to 1 when we apply the function. So the limit will not be 2 as it's supposed to be. All right? So that's great. So let's put it in practice. Let's write it down. So if you want, let's do it first with the number 2, and then we'll write it in general. So first, let us do x equals 2. Consider the sequence. I'm going to use the one Petro suggested. Xn equals 2 minus 1 over n, for n in the natural numbers, right? Now, what is h of that? Well, the first one is 2 minus 1, so that one is 1. Then it's 2 minus a half, that's also 1. 2 minus 1/3 also 1. They're all 1, right? That's the important thing. And if we have a constant function, the limit of that constant function is the limit of h of xn. Well, that's the limit of h of 2 minus 1 over n. Well, that's the limit of the number 1. So we get 1, right? But 1 is obviously not the same as h of 2. And that's it. That's a proof that this function is not continuous at 2. Okay. Now the same proof works if you pick anything other than 2, right? I mean, the number 2 had nothing to do with this proof. So we can do it in general. So in general, if x equals m belongs to the integers, consider xn to be m minus 1 over n. Note that h of xn will be, well, it's a number less than m, so it's m minus 1, right? It is m minus 1, therefore, the limit of h of xn is the limit of m minus 1. Here maybe I write n goes to infinity because we have now 2 variables so that you won't get mixed. And this is obviously m minus 1 because it's a constant. And m minus 1 is different from m, and m is h of m. So that's it. That's a proof that the function is not continuous at the number m when m is an integer, right? Oh, great. Now, to do the other part. What's the other part? The other part is to show that it is continuous. Let's go back to the graph. So for every other number, right? So if you pick any other number that is not an integer, say pi, right? Pi is somewhere over here. If we pick pi, then right here at pi, it is continuous, right? The function is continuous. So let's argue why that is the case. Okay, so how do we do that? We need to show, now let x be a number that is a real number. Let me call it c instead of x because we usually use x as our variable. So let c be a real number that is not an integer, okay? And we need to show that that the function is continuous there. So what is it that we need to show? We need to show that for every epsilon greater than 0, there is some delta greater than 0, such that if x and c are closer than delta, then h of x minus h of c is closer than epsilon, right? That's what we need to do. Let me put a box around it. Okay. Good. So how do we do it? See, we want this to be really close. And in fact, we can make them the same if you think about it, right? Because our function is made up of constants, constant pieces like this, all right? So maybe let's try it out with a specific one first so you see how we could do it. So let me pick a specific number. We'll make things easier on ourselves. So let's start with, say, 3.1. So let us try c equals 3.1. How good we do it for 3.1? Well, we need to show that for any epsilon, we can pick a delta so that if you're really close to 3.1, then this difference will be really close, less than epsilon, right? And here, like I'm telling you, we can even make it 0, right? We can make it 0. What should be the delta that we're going to use? Well, let's think about it. Let's recall what the graph of the function looked like. If you remember, so let me just zoom on the around 3 part. So let's say that here's 3 and 4 and 2. And we're picking 3.1 somewhere over here. And the function at between 3 and 4 is 3 and then all the way 4. And before is something else, right? I don't want to use the other part. I am only looking near 3.1. Yes? So all I need to do is, if you think about it, is pick as my delta something really small so that when I go up, my value is the same as the number 3, right? And what delta should I use? See, I don't want to go bigger than going away from 3, because if I go bigger, if I pick something like this, then I'm going to get these points over here that are less than 3. And for those numbers that are less than 3, the function is not 3 anymore. It's 2, right? It's the next level over here, right? I don't want to do that. So the delta that I'm going to use is 0.1 or anything less than 0.1, as a matter of fact, right? So note that delta equals 0.1 works. Why? Well, because if x minus 3.1 is less than 0.1, that means, what does it mean? It means negative 0.1 less than x minus 3.1 less than 0.1, correct? And if I add 0.1, what it means is 0 less than x minus 3 less than 0.2, correct? And in particular, it means that I should have added actually 3.1 on both sides is really what I wanted to do. So this is really what I want. 3 less than x less than 3.1 plus 0.1, 3.2. This is really what I want. Why? Because now I know that x is between 3 and 3.2. So what is h of x? H of x is 3, right? And if h of x is 3, then what is h of x minus h of 3.1? Well, that's going to be 3 minus 3, which is 0. And 0 is definitely less than epsilon. Doesn't matter what epsilon you give me, right? This is a very, in a certain sense, easy proof, because no matter what epsilon you pick, the same delta works, okay? All right, so that's it. We showed it. We can pick this delta, and it works for any epsilon. And I hope you can see the same thing would work for any number x, right? What would be the proof for an arbitrary number c that is a real, that is not an integer? Let's do it here. In general, if c belongs to the reals and not the integers, then there is a unique integer m such that c is between m and m plus 1, right? Any real number has to be between two integers. And as a matter of fact, this integer m is the floor of c. Okay, and then what delta should we use? So given epsilon greater than 0, let delta be C minus M, right? That's like the point 1. We're doing like, how did we find the point 1? Well, it was 3.1 minus 3. So this is the same thing we're doing here. We're picking C minus M. So we pick the delta equals C minus M, and then we go to a new blank page, and then if x minus c is less than delta, then what that means is that negative delta is less than x minus c, which is less than delta, or if I add c, it says that c minus delta is less than x, which is less than c plus delta, right? Well, what is c minus delta? Look from here. So c minus delta is actually c, is m, right? So this is m, and so this is m plus 2 delta. Therefore, h of x will be m, right? Actually, there's a slight difficulty here that I don't know if you realized. We sort of assumed that the number was close. See, there's something we're not doing quite well here. I don't know if someone already realized. So this works well. I actually didn't say it precisely correct. So let me go back over here. See, this wouldn't have worked if instead of 3.1, I picked 3.9, right? If I pick 3.9 and I pick 0.9, well, 0.9 is too big. Then I'm going to fail on the right side, correct? So I forgot something here. I should have picked the smallest from this point to the left integer and to the right integer. That's our safety zone, right? So let's actually fix that. Otherwise, so right here, I'm actually saying a lie. This may not be correct. I mean, it works for 3.1 because 3.1 was closer to 3 than to 4. But it's not going to work here for a general number if I pick this delta. So I need to fix it a little bit. I need to pick the smaller of two numbers. So delta, let's go back, will be the minimum of c minus m, and so and what? And m plus 1 minus c. You see what we're doing here? So c is between m and m plus 1. So we're choosing the smallest distance from c to m or from m plus 1 to c. And that's going to make it work, right? So the idea is similar. So now we just need to make sure that these inequalities are correct. So I should explain better why the floor of H is M, right? So this part is correct. So this part guarantees that the floor, this part right here, tells me that indeed X is bigger than M. But this may be too big. That's a problem, right? So now I gotta check that this doesn't happen. Well, and the way we check that this doesn't happen, so this is not M anymore. So let me backtrack. So therefore, X is bigger than C minus delta, right? But delta is the minimum of these two numbers. So delta is smaller than both of them. In particular, negative delta is bigger than or equal C minus M. And this is M, right? So that's one part. X is bigger than M. The other part that I need is that it is less than n plus 1. Well, I know that x is less than c plus 2 delta. C plus delta, sorry. And I know that delta is smaller than the second one here. So it's smaller than n plus 1 minus c. These c's go away, and this is n plus 1. Great. Now we got it, right? Now our number x is between m and n plus 1, thus h of x is m. And when we do h of x minus h of c, we get m minus m, which is 0, and 0 is less than epsilon, so we are done. So h is continuous at c. All right. Good. Any questions with this little example? Okay. Now I want to do another example. This is example 4.3.8. And this one, we're going to do this directly, but it can be done with sequences. In fact, you've already done it back in, can I show the top of the paper? This one over here, sure. So this next example, we have done it before with sequences, and it's sort of outlined. If you take a look at the book, we've done it with sequences. I can explain a little bit about that in a moment. But here's what we want to do. This example 4.3.8 is to show that the function root x is continuous on the set of numbers that are greater than or equals 0. All right. Now, like I said, we've done these problems before because as back in our chapter about sequences, we showed the following. We showed, so let me just say here, we call that as exercises in sequence chapter. We prove that if you have a sequence that approaches C, then root of xn approaches root of C. And if you know this, then you can use the sequence criterion for continuity, and then we're done. That's the proof that this is continuous. All right. So that would be one way of doing it. But I'm gonna do it a different way. I'm gonna do it, and this is to show you that every problem about continuity you can try to do directly, or you can try to do it with the sequences material that we did before. Either way is equally good. So this time we're gonna do it directly. So this is a second proof without using sequences. All right, so how do we do it? Well, it turns out that we need to do 0 separately. And 0 is sort of special because it's right on the outskirts of the domain. So let's start with 0. So first, let us do 0. C equals 0. So what is it that we need to do? We need to show that, for every epsilon, there is a delta, such that if x minus c is less than delta, and c is 0, so it's just this, x is less than delta, implies f of x, which is root x, is less than epsilon, right? This is what we need. Okay, and should be easy, right? Should be easy because there's a very easy way to go from this one to that one. In fact, they're if and only if, right? So to go from this one to that one, we simply square it. So that immediately suggests to you what should be the delta we should use, right? So if we want this one, then what we should do is pick as our delta epsilon square. Yes, so like I said, we're trying to prove this with a straightforward epsilon delta proof instead of using sequences. And we're gonna do first the case of 0 because 0 is different. 0 is the right at the end of our domain right here. So we need to do it in a different way. And I'm just writing what we need to do. I haven't done anything yet. To show that the function is continuous at 0, we need to show that for every epsilon, there is a delta, such that if x is less than delta, then f of x is less than epsilon, right? In this case, both we have minus c and minus the square root of c, but both of those numbers are 0. We're using 0. So, and then what I was saying is that there's a very easy way to go from here to here or from here to there, right? The relation to get, to go from square root of x and get x, all we do is square it. And to go from here to here, all we do is take the square root. So the relation is clear. So we should use as our delta epsilon square, right? So here we go. Now here's the write-up of the proof, at least for 0. So here's what we do. We say, let epsilon greater than 0 be arbitrary. Pick delta epsilon square, right? Suppose that x minus 0, which is x, is less than epsilon square. Now we take square roots. Then square root of x, or absolute value of x if you want, is less than epsilon. And absolute value of x and x are the same because in this case, our domain is only positive numbers. So we don't need to worry about that. So then root of x is less than epsilon, and root of x is the same as absolute value of root x. So we're done. We're done with when c is 0. All right. Now, what if c is not 0? Well, then let's write down what we need to show. If c is not 0, we need to show that for every epsilon, there is a delta such that if x minus c is less than delta, then root x minus root c is less than epsilon. So a little bit more complicated, right? It's our new goal. Okay, so now it's not so clear how to go from here to here, right? It's not as easy as squaring it or taking the square root. And there is still a relation to go from here to here, right? Which is sort of multiplied by the conjugate, which is what we need to explode here, right? So you would, to discover the delta that you should pick, you would start from this part over here and try to come up with this one, right? In some way. And so here's how it can work. So let's see if I want to talk a little bit about the discovery here or simply show you the proof. So let's talk a little bit about the discovery, right? Like how can we find out the delta that we need? So we start from here. So this is like our discovery work. So we start with this. This is what we want. That's an epsilon. Now what we can do is multiply both sides by the square root of x plus c. Right? And this is good because this becomes x minus c. Okay, so we sort of can control this one over here, right? We can make this one less than delta. So this tells you that delta should be, so we know that this one on top is equivalent to this one here. So all of this is an equivalency. So now we want something that implies this one, right? So we know x minus c is less than delta. So we should pick delta. So pick delta such that delta is less than epsilon over times x plus c, right? That's what we want to do. Now here's a little bit of a problem is delta cannot depend on c or on x, right? So, I mean, it can depend on c. It cannot depend on x. X is a variable. See, this should happen for any x. So I cannot say pick delta equal this, right? So I need to do something else. I need to pick, I want this to happen, right? I want this to happen because if this happens, then this one will imply the one I want, right? This is complicated because we're working our way backwards, right? So you want the opposite implications to work. You don't want this from here to work. That's kind of obvious because that's how we're sort of developing this. We want the opposite ones to work. So we want to find some delta that we can pick that would imply this one, right? So for example, here we can simply, I mean, x, and here's the thing where we separated x being different from 0. See, this is bigger than 0, right? So we know root x is bigger than or equal to 0. So root x plus root c is greater than or equal root c, right? So epsilon times root x plus root c is bigger than or equal root c times epsilon. So maybe this delta can work, right? We can pick this as our delta. This could be our delta. If we pick this as our delta, this number as our delta, well, this one is less than that. And then we have this one here. And if we have this one here, then we have this one. And then we have what we want. Is that clear? This is sort of how you can discover what is the delta that you want. And it is important. It cannot depend on epsilon and on x. So delta cannot depend on x. All right, so this is let's write it down. Let's see if we can do it. So how would it work? Let epsilon greater than 0 be arbitrary. Pick delta to be root c times epsilon. See, and this is important that we pick c is bigger than 0, because if c is 0, this doesn't work, right? You pick this, you're picking 0, and you need to pick a delta that is greater than 0. Okay, then assume x minus c is less than delta, right? Then this means that x minus c is less than root c times epsilon. And so if I factor x minus c, I can factor it as x minus root c times root x plus root c is less than root c times epsilon. Good. So now I divide by root x plus c. Which doesn't need absolute value bars because it's positive, right? And then the end of the proof is to realize that this number is bigger than the one on top. So this is actually less than 1, right? And this is because root x plus root c is bigger than or equal root c. And we're done. All right. Questions so far? See, I know we're sort of going slow with these examples because I want you to show you how to actually figure out the delta and the epsilon for this particular problem. What delta works for a particular epsilon, depending on the particular problems. There are other ones like these that I highly recommend that you look at, right? So one that is very instructive if you want to practice and get better at this, instead of trying the square root, try the cubic root. That's a very instructive one. Try the cubic root of c. All right, and I think let me just check briefly on our book. I think is one of our problems right here on our homework problems. I believe is, yeah, number 1, right? So exercise number 1 will give you a great practice at this one over here. So try cubic root, and these are the things that can be helpful, right? You first need to do 0, and this identity will be useful. Just as in this case, we use the fact that a plus b times a minus b was a squared minus b squared. Here, the identity you want to use is this one over here, the one that I just highlighted. Okay, moving on. Let's get to this next theorem, which it's also left as an exercise, is right here. 4.3.3, it says supply a proof of theorem 4.3.9. So I'm gonna do that right now. So in a sense, I'm gonna do a little bit of your homework. I'm gonna do part A, but I'm gonna leave part B for you to do. So I want you to still do the proof of that theorem using sequences, all right? But I'll do it with epsilons and deltas. And here is the theorem. So since I have this already here, let's just put the theorem right here. Okay, so what is this theorem? Well, it's about composition of functions. So last class, we saw that the sum of continuous functions is continuous, the product of continuous functions is continuous, the quotient is continuous as long as you don't divide by 0 in that domain. All of that happened. So this is the additional one we need to have, and this one is for composition of functions. So I'll show you a picture in just a moment. But this part over here says, if you have two functions, f and g, and f goes from set A to the real numbers, g goes from a set B to the real numbers, and f of A, the domain, the range of the function f is inside the domain of B, then the composition will be continuous, assuming both f and g are continuous. That's essentially it. All right, so let me show a little picture of our situation here. The picture to have in mind is that we have two functions. Let me go back to the page. We have two functions here. One of them is the function a, so we have our domain A. and we have B. And from here to here, we have the function f. And when you map, and the property that we have in our theorem is that f of a, the range of the function f is inside B. So when we send a with the function f, goes somewhere inside here, right? So this is f of a. See, so all of these goes inside here. And then we have the real numbers over here, and this is the function g. And so the important thing is any number c that you pick here goes in here. That's f of c, goes inside this part. And then from here to here, we get g of f of c. That's the composition, right? So that's what we need to show. We need to prove that. Assume f from a to the real numbers is continuous on A, and G from B to R is also continuous. Well, we only need at a specific point, but so let's say that this one is continuous at C, and this one is continuous at f of c. Show that the composition, so you first apply f and then apply g, is continuous at c. So in other words, the composition of continuous functions is continuous. All right, so that's what we need to prove. How do we do it? Well, let's start by looking at what we have here. So what is the meaning of these two properties, right? Let's write them down. So let me number this one star and this one double star. So here's a restatement of star. A restatement of star is the following. It means that for every epsilon, there is a delta such that if x minus c is less than delta, then f of x minus f of c is less than epsilon, right? I just wrote the epsilon delta definition of continuity at C. Now let's do the same for double star. Double star says for every epsilon, let me call it epsilon 1 to make a distinction. There exists some delta 1 such that if, and let me use a different variable here, y minus f of c less than delta 1 implies g of y minus g of f of c less than epsilon 1. All right, just wrote the definitions. I haven't done anything. These are just the definitions, and I was just a little bit careful here to use different variables so that we don't get confused between the two of them, right? Because the epsilon for one may not be the epsilon for the other, or the delta for one, the delta for the other, or etc., right? So we use epsilon and delta here, epsilon 1 and delta 1 here, and I even changed the x's over here to y's. So you see that, you know, all of those variables can be different, okay? And now let's write down what we want. We want, what is it that we want? We want for every epsilon, epsilon 2, there is some delta 2, such that we want the composition to be continuous at C, right? So we want that if x minus c is less than delta, then g of f of x minus g of f of c is less than epsilon. This is what we want. Right? And I hope you can see how we essentially, we got it, right? I mean, we can use these two, sort of like do a bridge. So go from here to here, and then this one will be this, and then imply the other one here. All right? Should be actually quite straightforward. So this is what we need to do. We start with an epsilon, and the epsilon that we have here, oh, this should be epsilon 2. This epsilon 2, we put it as our epsilon 1, right? And then we know that for that epsilon 1, there is some delta 1 that makes this happen, that this one implies that one. Then we use that delta 1 as our epsilon here. And for that epsilon, we know there is some delta that makes this happen. And then this, if this happens, then this one is actually the same as this one, which implies that one, and that's what we want. I hope that makes a little bit of sense. If not, let me just write down the details that should clarify things. Let me see, just a moment here. Yeah, I lost the chat. Okay, good. So let's do it. Let epsilon 2 be arbitrary. Okay, this epsilon 2, and then let epsilon 1 be equal to epsilon 2 in double star. Then by double star, there is delta 1 greater than 0, such that y minus f of c less than delta 1 implies g of y minus g of f of c less than epsilon 1. And remember, epsilon 1 is epsilon 2. Okay, I'm going to need start. Okay. Good. All right. Then what? Well, then we use also this delta 1 in star. So let epsilon be delta 1 in star, in this one over here. So this epsilon will be delta 1. So then I can use this one. So there is delta greater than 0, such that x minus c less than delta implies f of x minus f of c less than epsilon, but this is delta 1, right? And we are done. If you can see, all I need to argue is that I'm going to use now y equals f of x in here, right? So combining these two, let me call them 1 and 2. From 1 and 2, if x minus c is less than delta, then f of x minus f of c is less than epsilon. And then setting y equals f of x, g of f of x minus g of f of c is less than epsilon 2. So we are done, right? So we found a delta. That delta is delta. such that when x minus c is less than delta, we first get f of x minus f of c is less than delta 1, but then that implies that g of f of x minus g of f of c is less than epsilon 2. And that's it. And we can say thus g composed with f is continuous at c, right? So essentially, we use the delta from one of them as the epsilon for the previous one, right? And you can see that this can be iterated. So we can do the composition of several functions to create more and more continuous functions, all right? And this is the basic. So using this composition together with the addition and the multiplication, you now can get a huge number of functions that you can prove are continuous, right? Because, for example, we already ascertained that the square root function is continuous. We already know polynomials are continuous. So then we can now argue that the square root function of, so let me write it here, tons of examples of continuous functions. E.g., root x is continuous. And this one is continuous. G of x equals, say, x squared plus 2 over 3x to the cube minus 7 plus x on its domain. Thus, this new function, which is the square root of that, is continuous, right? Because this one is the composition. It is f composed with g. All right. Questions? Good. So, like I said, you can also prove the theorem we just did with sequences, and you should definitely try it out, right? It will give, it will be very straightforward and easy as well. This composition theorem is actually turns out to be quite easy. Okay, so I want to talk a little bit in the 10 minutes or so that we have left about the next section. So about to motivate a little bit what we want to do for the next section 4.4. And the question here is, we want to know what properties, this is really the question we want to answer. What properties, and by properties I mean topological, are preserved by continuous functions? That's essentially what we want to talk about. And so in other words, let's say that we have some function that it is continuous, right? So let f, say, be a function from a to the real numbers, continuous. And here are a few questions. Say I have some subset of A that is some topological property, say open or closed, or what other ones we know? Well, the only other one we went through is compact, right? Does it follow that when we apply F, the answer is also open, or is also closed, or is also compact? Those are the questions we want to answer. So consider B a subset of A. Here are my questions. If B is open, does it follow that f of b is open. If b is closed, is f of b closed? What about compact? Those are the questions we want to go through, right? What properties are preserved by continuous functions? So let's start talking a little bit about the first two, right? So what do you think? Let's start with this one, open. So we have an open set. Does it follow that the set is open? The image is open, right? And I'll make it even easier for you. I'll give you a specific function. So I'm gonna pick an easy one, x squared. That's continuous, right? So think of some domain here. Yeah, Kimberly said no. So what would be an example? What b should we consider? So I got a couple. So Kimberly said -1, 1. So if b is the open interval, -1, 1. That's open, right? Yeah, it's an open interval. Is open. And what is f of b? What happens when you apply the function to -1, 1? Let's see a little picture over here. So it's x squared. Yeah, 0, 1, right? So we have this parabola. We're doing from -1 to 1, but open. So when we go up, we don't use 1. Well, we do use 0. So our domain, our range is from here to here, without including 1. So it's 0, 1 open on over here, right? It's not open. Not open. It's also not closed, right? So there's not a real chance that this will work. It didn't even work with a simple function like x squared. So that was a hopeless question, right? So it's not gonna happen. It's not true that if we have something open, it's gonna go to open, right? So this is not preserved, and that makes us sad, right? Because it's always nice when you have properties that are preserved. It's always nice when we have properties that are preserved. I repeated that because it said that the internet was a little bit down. All right. How about closed? So could it work with closed? And again, we can see one thing we could do is try to look at the complement, right? See, if you know already that it doesn't work for open, then I don't think it's going to work for closed, because we can look at the complement. See, the complement of this set is closed, and the function of the image will be the complement of this one, and the complement of this one will not be closed. So that's one way of doing it. If you want another example, here's another function. This one is 1 over 1 plus x squared. And this time I'm going to use 0 to infinity, which is closed, right? This is closed. It's a closed set because it's a closed interval. And this time the graph of my function looks like this. Something like that, right? And when we do it from 0 to infinity, from here to infinity, Well, the image is from 1. We do include 1, but it approaches 0, right? You know, it gets closer and closer to 0. So f of v is actually open on 0, closed on 1. So again, not open, not closed. Not closed. So our property fail in a big way again. All right. Okay. So that's sad again, except that we still have one left here, right? The compact set, and that's gonna be the happy story here. It turns out that this property is preserved for compact sets. So if you have a continuous function and you look at the image of a compact set, the image will be compact. All right. So the reason this one doesn't work is because it is closed, but it's not bounded. Had it been both closed and bounded, then it would work, right? Then we could make it into something that is, the image would also be closed and bounded. And that's where we're gonna pick it up next week. We'll pick it up right there on section, we'll start section 4.4, okay? So I'm going to stop our session soon. Let me just make sure that there aren't any questions. Does anyone have a question here before we stop for today?
My question is just related to the exam.
Yes.
So initially, I remember you said we might just only take a final exam and not exam 2, but now it just looks like we are going to take exam 2, correct?
Yes, I think we should. I think it'll be better for you, you know, have more possibilities to,
Okay.
yeah.
And as far as difficulty, will it be more difficult than exam 1 due to the fact that it's a take-home exam, or?
Ordinarily, that's what I would do on any take-home exam, but as a matter of fact, no. The exam will be pretty much like the same type of exam you would have gotten on a regular test. We were asked to not do any of that, you know, not, I mean, consider that we're all under stress and it's harder, right? So
Right.
no, the exam will be equivalent to the one we already had. And you're going to have an entire day to do it. So there's one difference though. We're not, so whatever day we had for the test, we're not having the test at that particular time. We're having regular lecture at that particular time. We'll do a review, so you can bring your questions. Then later on that same day, I'll assign the test. I'll put it on Canvas, and you'll have 24 hours to do it.
Okay, so if it's still April 23rd, April 24th, it's not going to be extended.
That's correct.
Okay, that sounds great.
Yes, and I'll provide details on how to upload your completed test on Canvas. It could be a PDF, or you could take even pictures with your phone and just upload page by page, whatever you prefer. It's gonna be easy. It shouldn't be a problem for you guys.
Okay, and it still covers chapters 3, 4, 5.
Yes.
Okay, perfect. Thank you.
How about quizzes? Still, what's going on?
We won't have any more quizzes, I think. It'll be difficult to do that.
Can we submit our homework, maybe like to prove? I mean, I just thinking as extra credit, I don't know.
You can still work on the wikis, right?
Yeah.
Okay. And that will be your way of getting additional credit. But to be honest with you guys, I think most of you are gonna do better considering the setup. So, and I would expect you guys to do considerably better. You know, tests are obviously easier if you have more time to do them. So don't worry too much about the grades, is what I'm saying.
Okay.
Sounds perfect. Thank you.
Thank you.
All right. See you guys next week.